of Mobileye, Shai Shalev Schwartz. And really, we're going to get a very in-depth technological overview of what we think is really one of the most exciting companies in the space of ADAS. And then, as we're going to hear, progressing towards something that looks like full autonomy. Now, many of you know Mobileye, so I'm going to give a very brief overview. But for those of you who don't, global leader in ADAS perception and system on chips with over 70% global market share in ADAS. Mobileye pioneered the industry with the first front-facing monocular camera in the early 2000s and has grown that offering from basic functionality such as forward collision warning and automatic emergency braking towards really having now an end-to-end navigate on pilot solution. Mobileye works with almost all of the largest global OEMs. There's only a few exceptions, but these include Volkswagen, Ford, BMW, Stellantis, Nissan, and so forth, and most recently, Toyota. Now, Professor Shai Shalev Schwartz, the Chief Technology Officer, leads software development for both ADAS and autonomous driving. He works alongside Amnon to develop Mobileye's responsibility-sensitive safety, RSS, as we're going to hear about, a policy methodology, as well as REM, road experience management, and their proprietary crowdsourced mapping technology. So, Shai, thank you so much for joining us today. I feel like we're going to get a mini masterclass in everything AI and ADAS. So why don't we start off? My intro, it doesn't do you justice. Could you talk a little bit about your history at Mobileye, some of the work that you've done over the last couple of years where, we knew a little bit less about you. You guys kind of operated as an amazing silo within Intel, and now you've come back and we see some of the fruits of that, particularly in supervision, RSS and REM working together, for that supervision to chauffeur solution. But I would love to hear about, what you're working on, and, what's to come from Mobileye.
Thank you, Chris. It's really a pleasure to be here. So let me start by saying that these are really exciting times for AI developers. I'm researching AI for more than 2 decades, and during this time, I've had the privilege to witness and participate in 6 AI revolutions, where 4 of them happened just in the past 5 years or so. My role at Mobileye is multifaceted, but if I were to distill it down to its essence, it would be to ensure that Mobileye's technology strikes the best balance between, on one hand, developing and harnessing cutting-edge technologies, while on the other hand, doing things right despite fleeting industry trends and hypes. So in order to illustrate it, Mobileye was first to introduce a deep learning-based product on an embedded system. It was in 2014. On the other hand, we challenged the industry norms in 2017 when we released a paper outlining our unique approach to ensuring safety and scalability of autonomous vehicles. This approach is now encapsulated in our supervision system, and it consists of the following principles. First, the creation of a foundation layer capable of navigating anywhere using a camera-based technology and cost-effective computing. Second, the large-scale mapping of the entire globe through an automated, crowdsourced process that leveraged Mobileye's ADAS prevalence in millions of vehicles globally. Third, the design of a driving policy layer that is provably safeguarded by a transparent mathematical model. You mentioned the RSS model, and we will say more about it later. And fourth, redundancy layers, which necessitate additional sensors and or compute that can be added incrementally to extend the period between perception system failures. This approach enables a gradual shift from hands-off to eyes-off driving, and from a narrow ODD to a broader one. That is making progress incrementally rather than a moonshot. We believe this is the most effective pathway towards consumer-owned autonomous vehicles, and we are encouraged by the positive reception that we get from our customers.
Perfect. And Shai, so I set up the fireside chat to kind of go into each of those levels of the technological pillars as you laid out, because sometimes, and particularly with a lot of us generalists and investors and people not with your background, we always want to know what makes Mobileye special at each one of those steps. So if I think about that competitive moat, it really, in my opinion, starts with the base perception technology. So can you talk about how, from a single monocular camera, you're able to identify objects on the road, with what appears to be much higher accuracy than others, because others have attempted to do it, and we can go over the long list that thought they can get to automotive grade, but never got to that last 1%. And so what is some of the special sauce that makes Mobileye, so competitive on something that you probably have almost perfected over the years, but just on base level camera?
Sure. So this is indeed a difficult task. Despite what people think, you can look at demonstrations of object detection systems. It looks very, very impressive, but there are additional things that makes life complicated, and mainly there are three reasons. First, objects in reality are in the 3D world. On the other hand, cameras view a projection of these objects onto a 2D plane, onto a two-dimensional plane. This is called the image space. By doing this, we lose information. We don't know where is the position of the objects. So even if we perfectly detect the object in the image space, we still need somehow to lift it into the 3D world. And not only to say what the position of the object in the 3D world, we also need to estimate its full kinematic state, meaning its velocity, its heading, etc. So this is one problem, the lifting from the image space into the 3D world. Second, AI, and in particular machine learning, are the best approach, we all know. These are the best approach to object detection. These are really great tools, but machine learning is inherently a statistical approach. And as such, it suffers from the long tail problem. I mean edge cases. So it is maybe easier today to build an object detection system that detects regular cars at a single geography during daytime. So you can see a demonstration of such a system. But making the system work for all types of objects, globally, day and night, at different weather conditions, and for all sorts of weird objects, this is a great challenge. So this is the second issue. The third issue is that in order to be competitive, the system must run on an extremely cost-effective computing device. So maybe you can come up with a very good system, but it requires a server in the trunk. It will not be competitive with small chips that sits on the windshield, and also the price point will not be relevant. So the combination of all these three issues are what makes the problem difficult. And Mobileye basically solved the three systems. It wasn't easy. It took us a lot of time, but we have proprietary algorithms for lifting 2D image space into the 3D world. We perfected machine learning for object detection, including building a huge and massive data set from all geographies and all type of weather conditions and all different type of objects, even the weirdest ones, including tools to enable us to search in this huge data set, etc. All of this we perfected among many, many years in which we are playing in this field. And third, we have our own chip, and the software is tightly integrated with the chip. So we can build a solution that in terms of cost effectiveness is really, it's very, very hard to beat it.
So if we work off that base perception and we work into the, sort of the next two pillars, driving policy, we'll talk about RSS, and then we'll also talk about the robustness of REM. So if we start at RSS, can you talk about how that came about? You talked about 2017, how you decided to do something that was both, end to end, but within sort of some version of a rules-based framework. Could you talk about how it was developed, and then also the benefits of having something that can be sort of, objectively checked and scaled, for things like liability and basically consumer trust?
Sure. So I brought deep learning to Mobileye at 2013. This was 1 year after the seminal paper of Krzyzewski, Sutskever, and Hinton in 2012 on the ImageNet challenge. And it was really a really fast integration into Mobileye system. And already in 2014, we had on-road deep learning on our chip. So this was really fast. And then I figured out that driving policy is the next big deal in order to make the next step. This was around 2015. So the approach of machine learning that worked so well for the perception layer was an immediate candidate also for the driving policy. And the right tool for driving policy in terms of machine learning is what is called reinforcement learning. Mm-hmm. It's not supervised learning like what we use for perception, because driving policy has a closed loop nature, meaning that what you decide to do affects other road users. Okay, so you cannot just look at offline data and figure out what to do. It's like learning how to shave from watching YouTube videos. Okay, you want to try it and without trying it out, it will not work. So I had a lot of work as well as some novel algorithmic approaches how to use reinforcement learning for the driving policy problem. And we tried many things, and we had simulations, and we let the simulation run overnight, running millions of events, and came in the morning after that and saw that it worked really impressive. There was just 2 or 3 accidents. A minor thing, but overall it worked very, very well. Of course, 2 or 3 accidents, it's not a minor thing. So we needed to adapt the algorithm and rerun. So we did it, and then we worked hard all day and came up with, boosting the performance and come up with another thing, and then again, let it run overnight. And again, it worked really, really well, but there were, again, 1 or 2 edge cases, and we had accidents. And this goes on for about a month. So after a month, I figured out, maybe this is not the right approach. Okay, so what I figured out is that machine learning is inherently a statistical approach, and we cannot afford lapse of judgment in driving policy that statistically happens rarely, but still happens. Just I figured out it's not something that society will accept. So we need to replan. So on one hand, we want to keep the benefits of machine learning because it's a great tool. Mm-hmm. On the other hand, we need an additional factor. And then came the idea of RSS. Maybe we can say, okay, the decision-making will be based on a neural network and machine learning and all the goodies that come out of machine learning. But we need a safety net. We need something that will safeguard us and prevent us from doing something really stupid. And this is one element that led to the development of RSS. The second element that led to the development of RSS was that driving policy decisions are inherently subjective. Okay, if you are sitting on the passenger car and someone else is driving, you always, or at least I don't want to say you, but I always have criticism on the driver. Why did you do that? You should have done that. Okay, and it's really a subjective thing. So even if our neural network would be perfect and there will be an accident, then we'll start an argument. Mm-hmm. Did you do the right thing? Maybe the judge will say, okay, I would have done things differently. You were reckless. Okay. So I wanted a language that will enable to clearly define in advance what does it mean to be safe and what does it mean not to be reckless? What does it mean not to have lapse of judgment? Can we set the rules of the game in advance and not in the aftermath? So this was the foundation. This was the seeds that led to RSS. So what is RSS? RSS was a mathematical way to provide a transparent language for objectively agreeing on what is allowed and what is not allowed. And what we managed to do is to mathematically guarantee that if we agree on the rules of the game, then we will behave sanely. This makes the validation process of driving policy feasible, because if you rely only on statistics, because of the closed loop nature that I mentioned before, mm-hmm. the validation process becomes not feasible. And then you go to a game of, I drove millions of miles, he drove 2 millions of miles. Both of the million and 2 million is not enough. Mm-hmm. I think we need to aim higher. And RSS was our method to say, we don't want to play with statistics in lapse of judgment. We just want to set up the rule of the game and follow it and make sure that we are never going to do something really stupid.
So it's almost you will still be using your deep learning, machine learning, reinforcement learning, but there's a do not violate an Asimov's sort of rules of driving that sits on top of that deep learning, so that you can't violate what would be an extremely unsafe state.
Exactly.
Okay. That was one of the best explanations I had for RSS. I really appreciate that, Shai. Can we talk then about what REM adds on top of both RSS and base perception? I tend to think of it as sort of a practical, elegant way of vehicle to infrastructure, and you can scale it because it's using your level 2 cameras. But what does REM add to the robustness of the systems, and when does it become really important? Is it important even as low as level 2 plus? And what does it add as you move up the autonomy stack?
Yeah, sure. So there are several advantages of REM. I think it was phrased very, very nicely in the previous meeting we had with some of the investors. When you are driving from home to work, you know the way, you are doing it fluently. You don't need to think a lot because you're already familiar. You know exactly where you are going and what you're doing. When the same driver arrives to some new country, and this is the first time he's trying to figure out what to do, he will be much more hesitant, make more mistakes, and he doesn't know this area, and he will be able to drive. It's not that he will not be able to drive, but he will not drive like a local. And REM is a tool that enables us to drive like a local everywhere in the world, because it's not just a map, it's a summary of the crowd behavior at every place in the globe. So it allows us to adapt to the culture and exactly the rules of the game and the rules of the road and the typical behavior of other road users everywhere in the world. Now, is it necessary for driving? Of course not. We are working and we can drive without a REM map, but it will be like putting you in a foreign country where you try to drive for the first time in some area. You don't have memory of, oh, I did this drive for thousands of times. I know how to do it. I know exactly what to expect. I know exactly what are the dangers that are waiting for us. So this is one element of the benefit of REM. Second element is we are a great believer in redundancy. Everything that we do, we want to do in different ways. So in object detection, you can say, okay, I detect objects using the cameras, I detect them differently using a radar, and I detecting them differently using a LiDAR, if you have all of these three sensors. Of course, supervision now is just cameras and a radar, no LiDAR. We still drive perfectly, but we will drive much better at a higher level of accuracy if there will be another redundant system that can be added to the stack. Same thing happens with understanding of the road. Where are the lanes? Who has a priority in a junction? What is the speed limit? Etc. 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 Many things that are static in the world, we can figure them out in online every time from scratch. This is a perception layer. But if we have a REM map, we know all of this using a different redundant way, which is actually even better than the way of looking now at the road signs and the lanes. Again, take the example of driving from home to work versus driving in a foreign country. You don't need to look at the traffic signs in order to know what should be the speed limit at every piece of road on your way from home to work. Okay, you just don't need to look at anything. You know it.
And Jai, because I think the way you phrase it is really important. I think we all think that it's adding an elegant camera map, but it's really also about the drivable path, right? That's being a local. You know that every turn, this is how people were making the turn. Can you talk about how that increases the more REM partners you have, the latency of how when the drivable path is observed to have changed, meaning something has changed. There's a construction, there's an accident. I don't know the exact number, but you're approaching something like a dozen REM partners, both harvesting and users. As that number goes up, do you get more functionality out of REM because your latency can go down from 7 seconds or X number of passes to build the updated map? So a little bit about that, how it scales the more people who use REM.
Yeah. So obviously, what are the main problems with building a map? It's not a new thing. People were building maps for a while, and even high definition maps. And usually, people what they did, they took a vehicle, a specific vehicle with many sensors on it, mainly lidars because they are perfect for building maps, and just drove on every road that they wanted to map. And then in an offline process build a map. What's the problem with this approach? So there are two main problems with this approach. First, even if you invested a lot of time and money in mapping every road in the world, roads are being changed all the time. So you will not know it until you will send your dedicated mapping car again to the same area. And then it becomes not feasible to have updated roads of the entire road. So you want something that will know that road has been changed, and you want to know it fast because you don't want that some road has been changed and you need to wait half a year until your mapping a specific vehicle will reach there again. So for half a year you will have a road which is wrongly mapped. You want to be able to figure it out as quickly as possible. And REM approach, which is crowdsourced, is naturally a great solution for this problem. We call it TTRR, time to reflect reality. So the more vehicles that are harvesting information for REM, the shorter the time to reflect reality becomes. Okay, because if you have many cars, then the first one that arrives to a construction area will be able immediately to tell the cloud that something has been changed at that road, and then all other vehicles, autonomous vehicles that will reach there will already know to expect that something has been changed in the road system. Okay, so the second element is using more from the map relatively to a traditional HD map, and this is, like I mentioned before, the map is not just a description of where are the lanes and where are the traffic lights and stuff like that. The REM is also a description of how people are driving on these areas. Mm-hmm. And again, the larger the crowd, you get a better statistics of understanding how the crowd behaves. And so again, with more and more cars on the road, you are not only harvesting the location of static things in the road, you also harvesting the behavior of people that are driving on these roads.
And then Chai, when I think about, one of the only remaining, bottlenecks to REM, particularly with customers that know your capabilities, right, and see that added, features and robustness that you can add through REM, it seems like from the outside, REM is a complex legal agreement, right? You're using a level 2 camera, you're anonymizing the data, right? You just want to know car A, you don't care who's in car A, you just want to know the path it takes. And some of these agreements have taken a while to kind of get over the line. Is that still sort of the main bottleneck of OEM adoption? Is there other technological hurdles? But I'm constantly looking for large OEMs like the Toyotas of the world to adopt REM. And I'm just curious, has since the beginning, 5-6 years ago, is there a quicker time for customer adoption because you've gotten around and you're using sort of the same frame agreements from OEM to OEM, because these are large organizations that tend to move slow?
Yeah. So first, just to be honest, we are working on REM for more than 5 years. Mm-hmm. It's a really difficult task. Okay, it's not easy at all. Okay, building a map that will be 100% correct everywhere and will reflect what we want to achieve from this map is a really difficult task. So it's not something that you take 10 people and let them work for a year and then you have a map. It's really a big AI problem. There is a lot of AI that is being used in order to do this. You can think about it as a puzzle because you get bits and pieces, okay, and you need to glue them together into a coherent view of the road, and it's really a difficult task. Furthermore, you need to figure out what you want from this map. Again, tight integration between what is in the map and what driving policy needs. Okay, if you go to a map maker, okay, they don't know what they need to provide to you. Okay, for sure they know the basics. They know that they need to give you lanes and they need to give you maybe a location of traffic lights. But since we are doing the driving policy, we know of many other things that are very, very useful to have for an efficient driving policy if you plug them into the map. So even if you have all the information that Mobileye is using for building the map, understanding what needs to be done and do it properly is a big task. And last, you can think about how you make this approach of constructing an RSD and sending it over to the cloud efficient and in terms of economic value per money, you want it to be valuable, right? So the thing is that we are leveraging many things that in any case Mobileye is doing for the ADAS applications. So for the ADAS application, we need to figure out where exactly are the lanes. Mm-hmm. We need to figure out for advanced ADAS applications, things like very accurate ego motion, how the car behaves, understanding how exactly the car moves on the road. These are things that we need to figure out for our ADAS in any case. So we are doing the heavy compute of doing it in any case. And then we extract just a really tiny amount of information, and then with the puzzle work, construct the mapping. So if other player is getting the feed of the images, so yes, if he takes all the images and upload them to the cloud, then he has all the information. But then first, it's very expensive to upload all the images, and secondly, it doesn't something that it violates privacy. That doesn't something that you can do at scale. Okay, because we are in any case having millions of cars with our ADAS system on the road, we can get information on scale. Now, information on scale, getting back to the advantage of millions of cars, is reflected in time to reflect reality, and is reflecting in our ability to detect hazards in the cloud very, very early in the game. So there are many advantages that only a player that can do REM on a very, very thin layer of communication between cars and the cloud, and without putting on the car extra need for compute. This is the only way to be a player at the level of the REM technology.
And I guess that's also why you're focused on large geographies, but Japan, Europe, US, because that way that TTRR is optimized for first applications, and then you can continue to theoretically go anywhere, but you want that TTRR optimized in the specific geographies where you're going to operate first.
Chris, I'll just add on kind of one point. I think that at the beginning, back in 2016, 2017, kind of convincing the OEMs to kind of allow us to extract data, you needed to create a framework for ownership and kind of what the OEM would get in return. I think we've done that, right? And we have enough OEMs providing data and kind of the platforms that are, that have chips that are actually sending us data, that as more vehicles are produced, you get more data points on a continual basis. But, we were able to extract enough data for, that would cover more than 90% of US and Europe roads, in about a year. right? And kind of at this point, it will just, more cars will lead to kind of more quicker data points, right? Getting that time to reflect reality even further down. So, we will certainly accept more OEMs to become, data harvesting companies, but we don't necessarily need it. Now the focus is more on, generating business wins for OEMs to utilize.
To utilize it, exactly.
Right. And so I think that's also, a lot of progress on that front. As VW already has a program. We're adding Ford this year, Stellantis, and there's many more beyond that. So that's really kind of what we're more focused on now.
And Dan, that's a really important point that to use the map, you don't have some of the same legal issues of harvesting where you basically need to anonymize the data. They are just receiving the drivable path information. So those REM agreements of pure users is actually an easier legal agreement.
Yes.
Yeah. Okay. Fantastic. Look, when we hear REM and users, we think future supervision users. So that's all extremely encouraging. I want to incorporate a couple of the questions online because they sound like two of my questions coming up. So I'm going to talk a little bit about SDKs, and then maybe we'll end on true redundancy as we move from supervision to chauffeur. So for SDKs, there is always this open versus closed debate, right? And what an OEM wants to do, where does Mobileye's work end and an OEM's work begin? And they want to, build upon RSS, build upon your drive policy, but also, how the car feels, right? There's a lot of different things, DMS, user interface. Can you talk about, the latest IQ chips, what they're able to do through SDK, software development kits, particularly with those OEMs that maybe have some expertise coming from robo down that want to build, decision or driving policy on top of supervision? Is that something that you see going forward? The last thing I'll mention is it does seem like this idea of collaborative steering, collaborative driving, like things like lane changing, where it's not me versus the computer, I'm kind of working with. However you want to answer, but it does seem like there's two camps. OEMs will just take your supervision, and then OEMs who will want to build on top of it.
Yeah. So I want to start by saying that supervision is not a system, it's a platform. Meaning that the same supervision platform can be on a Zeekr car, can be on a Porsche car, can be on other cars, and it will look and feel completely different. How we achieve this? We expose many parameters that control the driving behavior and the application layer, collaborative behavior of the car. All of that we expose it outside to the OEM, and then the OEM can tune the platform to build an actual system that meets the exact way how we want things to look and feel. Of course, what we have established as a basic layer that should be among everyone the same thing is first a perception layer, because it's facts. Okay, if there is a car here, there is a car here. There is no look and feel for whether there is a car in front of you and where it is. And the layer of RSS and the safety layer of the driving policy. Okay, again, these are baselines that should be in any supervision system. But all of the rest can be modified and adapted to the OEM liking. Now, the question of how to adapt to the OEM liking, some OEMs, and actually both Zeekr and Porsche chose this way, and I think it's a good approach, are going to work by taking this platform and adapt it to their needs, without the need to actually run additional neural networks or stuff like that on the chip. But with IQ6, we opened an SDK that allows some customers to even innovate on top. So they can have their own neural networks and code runs on the IQ with an SDK, where again they get the basic layers, and then the additional thing that they want to implement by themselves, they can build and innovate on top of Mobileye system. And this is also a valid approach which stems from listening to the needs of our customers, and this is something that we heard a lot from our customers, that they want to be in the game as well. They want to add their own neural networks and code that performs additional layers that will differentiate between one OEM and another OEM. And this is all good and blessed, and we support it.
Fantastic. Now, a couple questions coming in. So and it's a really important topic of true redundancy, right? You've talked about supervision. Well, basically, is sort of a training system for your chauffeur, where by adding a redundant perception OS of radar and LiDAR on top of camera, you can sort of hit that, the 10 to the 7th power in terms of what's needed to truly have minds off or eyes off driving. The questions that are coming in, what's interesting, we had Innoviz on just before, neighbors of yours in Israel, and they actually have some large wins with Audi and VW for their 905 program. And when we asked the companies, how do you think about Mobileye, where theoretically it's camera only, but some of these OEMs would love a redundant system, even if it's not true redundancy to the level that you want for level 4. They give a very positive answer. Seeing that they expect to be a LiDAR provider on many level 2 plus and level 3 programs, but that obviously they're going to work with the established camera providers who are also at that same OEM. The question I have is, I know in Chauffeur you want to have three perception systems, right? Radar and imaging radar and LiDAR and camera. But in level 2 plus, could there be basically a robust system that has a pretty affordable $500 LiDAR plus your supervision? Like, could that be a very nice bridge for a mass market system where, we know Chauffeur and we know that basically costs have to come down for a true redundant system, whatever year that is, in 26, 27, whenever Audi launches it. But long-winded question, in the meantime, could we have LiDAR and camera in supervision be actually a pretty strong system, the way we saw, there is a radar on the Porsche system that you announced?
Yep. So for sure, first there is a front radar also on Zeekr, and we use it, and there will be several radars on the Porsche, and we are going to use it as well. So for sure, we are going to use whatever we can. That's for sure. I want to maybe emphasize or maybe crystallize what exactly is this true redundancy approach, because people tend to think about true redundancy only in terms of validation, and I don't think that this is the strongest point of true redundancy in validation. So let me explain exactly what I mean. So you can think, okay, I have a strong system, I want to validate it, I want to make sure that it is reaching some accuracy level. So if I have two redundant systems and they are really independent, then I can multiply the probability of failures, and therefore validating on a smaller amount of data and just multiplying the numbers. So just as a quick example, which is not really accurate, but just for the sake of explanation, say that you have a camera system, you have a LiDAR system, each one has a mean time between failure of 1,000 hours, then combined together, the mean time between failure will be 1,000 times thousands, meaning 1,000,000 hours, okay? But this is not the big picture here, okay? First, you need to, in order to make this a big picture, you need to make sure that these are indeed independent systems and how you prove it, etc., etc., etc. It's missing the point. The main point here is not how you validate the system, but how you actually build the system. So I don't know of any AI solution that can reach 10 to the 6, 10 to the 7 hours mean time between failure. Not exist. Not GPT-4, not GPT-5, and not anything in the horizon can reach this level of accuracy. We have amazing AI technologies out there, okay? But the amount of this, the standard of this accuracy is unheard of in AI, okay? So the question is, if there is nothing in the horizon that can reach this accuracy, how you tackle the problem of building such a system? And for this, the answer is redundancy. And not only true redundancy, but redundancy all over the place. So actually in Mobileye, we don't just do true redundancy between a LiDAR system and the camera system. Even inside the camera system, every problem that we are tackling, we are solving in more than one way. Even the problem of vehicle detection, okay? Maybe the most streamlined problem in autonomous vehicles, just, figure out where are the vehicles on the scene, okay? Very, very well-defined, everything seems clear. A single neural network that will try to do vehicle detection will have failure points. This is the nature of statistical systems. Okay, so what we are doing, we are actually building more than 2 systems that aim to do exactly the same thing, detect vehicles in the scene. Okay, but we call it algorithmic redundancy. They are doing it with completely different algorithmic approaches. One approach is to use appearance-based, so you detect vehicles by how they appear in the pixels. Another one is geometry-based. You build a 3D representation of the scene, and then you just look for boxes that stick out of the road plane. It's 2 approaches which are very, very different. Okay, one approach can make errors of one type, and another approach will make error of different types. By building every system in different ways, this is how you get to high level of accuracy. So it's true within cameras, it's true within LiDARs, and it's true as a methodology for reaching 10 to the 7 by having different LiDAR system, different radar system, different camera system. And then when you combine all of them, they all have different modes of failure, and this is how you reach such a high level of accuracy with an AI-based system.
And then, Shai, in the way that you describe the MTBF, basically, camera in the second system, 10 to the third, we get to 10 to the 6, to 10 to the 7. In a lower system where they're not independent, but we add, onto your camera 10 to the third a LiDAR or an imaging radar, what does that add? I mean, there's some redundancy, but it's not independent. So how do I think about it in a dumb math guy to think about what that second system adds in sort of supervision?
So two answers. First, the systems, even if they're not fully independent, they are in some sense independent. And then all the failure points in which they are independent, you gain from them. This is one thing that you gain from these additional systems. Secondly, it's not just safety, it's also comfort. So yes, you can drive based on camera alone, but you get more accurate vehicle measurements, target measurements, if you combine it with a radar, and more accurate location if you combine it with a LiDAR. Every sensor has its own benefits. So for the comfort element of the system, not the safety one, you gain from the availability of additional sensors, even if they are completely, even if they are not completely independent of each other, because they cannot by themselves do everything they should. So there are a lot of benefits. More sensors always give you more power. Okay, and then it comes what you gain for the price. That's the bottom line. Question of leveraging them in ADAS system in eyes-on systems. The question is, do you really get enough advantage in the comfort of the system by adding these additional sensors?
Absolutely, and that was the variable benefits also above safety that I was missing. I think unfortunately we're out of time. I say unfortunately because I would love to pick your brain for a very long time. But thank you so much for coming to join. Dan, thank you so much for setting it up. For those of you on the line, you want to learn more about Mobileye, feel free to email the team. We can send you all of our 101 to help unpack and go into more detail everything that Shai went over, so you're not spending hours on Google trying to understand everything we just spoke about. And then also happy to put you in contact with Dan to learn more. So Shai, thank you so much for joining. Look forward to speaking again. Look forward to seeing you in Israel. And Dan, thanks so much for setting this up.
Thank you, Chris.
Thanks, Chris. Good stuff.
Great, everyone. Speak again soon.